Hello. Today we're going to be going through a presentation titled LSM-tree storage engines don't need to be complex to be exceptional. So a little bit about me. I'm Alex Gaetano Padula. I am an open source programmer. Some might call me an engineer. I'm the lead architect of TidesDB. I've been programming since I was pretty much a child. Um, I got my first computer very young and was very obsessed with it. In late 2022, I started to learn about storage, reading about data structures and the different systems, and by implementing them, I implemented B trees, disk-based B trees to distributed in-memory systems, to a variety of different embeddable LSM tree type systems as well. Just to learn, just to really learn, and each project taught me something different, made me question things, and fueled my curiosity. Nowadays, storage has become a lifestyle for me, and it's become my passion and obsession. So what's TidesDB? TidesDB is an open source embeddable um, storage engine. It's primarily written in C. It's licensed under the Mozilla Public License, version 2. So what does it mean to be a library? Well, you install the library and you can include TidesDB in any application that you're writing in C, let's say. TidesDB also makes it easy for you to generate like a foreign function interface in your favorite language as well, so you can generate that if you wanted to. TidesDB is high performance, low latency, and space efficient. It's optimized for fast write throughput. Uh, the fundamental structure, like the underlying structure within TidesDB is LSM based, so based on the log structured merge tree. TidesDB utilizes lock-free internals where applicable. It's designed for modern hardware, so lots of RAM and many CPU cores. Keys and values stored in TidesDB are raw byte sequences. TidesDB implements multi-version concurrency control, so minimal blocking on writes and reads. Let's continue on. There's one more piece here we can mention. TidesDB is adaptive, so the storage engine adapts to the data that you're actually putting inside of the storage engine. So that's pretty cool. So as I mentioned, TidesDB is optimized for fast write throughput. So what that means is sequential I/O patterns are very good for this system. So one of the downsides though is reads have to search through multiple sorted files. So there's that downside for reads. So why even build TidesDB today? Well, existing libraries are quite complex. They're quite bloated, right? They take a little bit long to compile. RocksDB takes quite a bit of time to compile on my system from source. Existing libraries like LevelDB, for example, were developed and designed in the 2010s. So they were designed for that era, not for today's standards. People want something portable with an easy API. That's very understandable. TidesDB is built on modern research, such as the 2022 paper granulating LSM trees granulating LSM tree compactions correctly, WSKey separating keys from values in SSD conscious storage, and SSI, which is explained initially in the paper serializable isolation for snapshot databases. So as of late, TidesDB 7 has shown superior results utilizing many cores comparing to the industry standard RocksDB, where RocksDB uses 306%, TidesDB pulls ahead utilizing 511% CPU utilization. You can get up to 5x faster writes, up to 6x faster reads and seeks, and up to 6x smaller databases, up to 30% less write amplification, and persistently low latency. So how do we do that? Well, TidesDB is built on some fundamental design pillars, such as we're lock-free where applicable. So some of our components are such as the block manager, skip list, transaction buffer, and clock cache are lock-free and atomic. We try to keep it simple where we can. It's designed for modern hardware, as we mentioned earlier, and we try to develop the engine in a way that it's portable and multi-platform first. So how does the system look like when it's embedded? Well, firstly, when you include TidesDB as like in your application, let's say, you can have many instances living in parallel, so long as they live in different data directories, which which you can configure when you open a new TidesDB instance. Each TidesDB instance can have many column families. A TidesDB instance requires at least one column family. Um, each column family has its own configurations, its own mem table, immutable mem tables, manifest, and disk levels. So disk levels have SS tables and SS table files. The mem table is a skip list paired with a write ahead log. Okay, the configuration is in any format. TidesDB has a few different workers that run in the background. One worker is the Reaper worker, which takes care of evicting uh, uh, essentially not as accessed SS tables. So let's say your max file descriptor limit is 512. You set it in TidesDB. When the system reaches 25% of that max, it'll start to evict. I mean, when it reaches that max of 512, it'll evict the 25% oldest or least recently used SS tables. The Reaper also takes care of um, caching the a syscall for time because TidesDB supports time to live, and time is used internally throughout the system, and that call is expensive and it does take a little bit of time, right? Like this is a very uh, slow thing to call in a hot path, right? Like a time. So we cache that with the Reaper, and we utilize that internally. Um, we have a compaction worker, a flush worker, and a sync worker. The compaction worker has a queue. The flush worker has a queue. They dequeue work across all column families. So they're shared between all column families. So work can be done in parallel. You can configure how many workers you actually want to utilize. The sync worker is a background thread that if you configure a column family to use sync by interval, it will essentially every n milliseconds um, synchronize the column families that are configured for sync interval, right? So syncing mainly the write ahead logs for the column families. We'll get into that a little bit more, but yeah. So internal components. TidesDB has a skip list as one of the main components inside of a column family. The mem table has a skip list, right? It's a probabilistic data structure. It's lock-free for updates, mainly lock-free actually, because deletes, we don't really handle deletes truly. It utilizes compare and swap with atomic pointers for retries. It implements multi-version concurrency control, so keys can have many versions. It supports seeking and bidirectional traversal, custom pluggable comparators. A deleted key, a tombstone in TidesDB is just a deleted version. It's just a new version with a deleted flag. Versions are prepended, and yeah, sequence numbers are utilized to see less than or equal to your this the visibility rules kind of play into here. So we pass the sequence number from the transaction level, the database level to the skip list, and we can see data that way. TidesDB uses a skip list, as I said, for column family mem tables on a sorted run to disk to L1. TidesDB traverses the skip list in order and writes the latest versions to a new SS table files. Another component in TidesDB is the block manager. It's lock-free, append only. It's utilized as IO abstraction for the redhead log, klog, and vlog files. Atomic position independent IO blocks are self-describing, so there's no fixed size to the blocks in the block manager. It utilizes fdatasync for Linux. Has a bidirectional cursor as well, so you can go forward and backwards for the blocks. The format is optimized, so for fast iteration. So each block has a header and a footer describing the data, like the length inside of the block. So if we start at the bottom, we can say, okay, how much data is inside that block? 500 bytes. Okay, we know how much bytes to read from header to header. So it's pretty cool like that. It allows us, essentially to iterate through the box very fast. Um, and also validate, right? So we have this backwards walk validation. So we can check from the footer checksum to see, hey, is this block actually valid? Was it completed and not, corrupted? And we utilize that, and we'll explain that further down the line. A block can only be 4 gigabytes in size. Okay. TidesDB uses a Bloom filter per SS table. A Bloom filter is a probabilistic data structure. It's basically we hit the Bloom filter, and the Bloom filter tells us, is the key here or is it not here? We implement it with a simple multiplicative hash implementation. The performance impact is 1% false positive rate, FPR, eliminates 99% of discretes for absent keys, which is pretty critical for performance. Let's see here. Yeah, so each SS table has a Bloom filter. They're kept in memory and brought into memory on recovery as well. They're rather compact, and it's one of the first checks we do before we go into an SS table. So it's usually the min-max key, the Bloom filter, and then the indexes, and then further down the line. We implement a buffer. The buffer, it's utilized as a transaction buffer, mainly for serializable transactions. It's lock-free. It has atomic state machines for each slot, generation counters to assist with ABA. And yeah, we utilize the buffers for transactions, active transactions in each column family during serializable isolation. The system really has to detect different conflicts for concurrent transactions, so the buffer assists us with that. TidesDB implements a clock cache. The clock cache is lock-free. It implements a clock eviction type algorithm. So we utilize this clock cache for blocks inside of a K-log because it's expensive to redisk, deserialize that K-log block, etc. Right? So if a block is pretty hot, we want to try to keep it in memory when we can, the 64 KB block inside of a K-log. So yeah, we mainly utilize this clock cache as lock-free, atomic, zero copy block read API. The cache divides into n partitions, and each partition has its own clock hand and hash indexes. TidesDB utilizes a queue, a first in, first out type of queue. As mentioned earlier, each compaction worker and flush worker at the database level can utilize this kind of a queue for its work. The queue has this dequeue, blocking dequeue, so it waits for work, and then once it gets work, it dequeues it, does the work, and then goes back around and gets more work. TidesDB implements a manifest at each column family level. So the manifest is used for tracking SS table and level details. It assists with TidesDB's recovery of column families. Commits, we implement areas like atomic commits. It's thread safe, self-cleaning, and self-compacting. So an idea of how this works is, during a sort of rent to disk, a flush, this will add a new SS table to the manifest. Let's say on compaction, this can add and remove SS tables from the manifest. The manifest is essentially like the source of truth for the column family's LSM structure. So I mentioned earlier, TidesDB has ACID transactions with 5 isolation levels, starting from read uncommitted all the way up to serializable. Serializable implements something called SSI, serializable snapshot isolation. The system is able to track read and write conflicts and detect pivot transactions. We don't maintain any kind of full precedence graph or perform a cycle detection. So false aborts are possible, right? They're possible. It's a trade-off for throughput. On false abort, you simply retry. And this is more of a simplified SSI. TidesDB implements well, it allows partial rollbacks within a transaction utilizing save points. So you begin a transaction, you write some operations to it, you create a save point, you begin writing more operations to the transaction, and you can roll back to that partial state. So TidesDB has 3 different sync modes: sync none, sync interval, and sync none, sync full for column families. So sync none, every write won't be synced, right? But TidesDB internally, when there's like an SS table that's been completed or a compaction with an SS table that's been completed, these kind of things, like a write ahead log on shutdown, fsync is utilized there, but on every single write, we don't do that unless you have sync full set for the column family. The sync interval is, if you set that for a column family, then that column family is going to be periodically synced in the background in the sync thread at the database level, right? You set the interval at the database level as well, and n amount of milliseconds. Comparators, we offer 6 default comparators, and you can register your own custom ones as well for domain-specific stuff. It's a cool feature. The comparators are used for the skip list, the sorting within SS tables, indexes. So yeah, big deal. Comparators, they're plugged in internally to the engine. TidesDB has seeking and iteration. So this is a fundamental feature. So being able to seek to a key, go forward, go backwards, it's a big deal. We abstract all the sources away, right? So you don't see the active mem table, you don't see the immutable mem tables, you don't see the levels in the SS tables, right? You don't see any of that, the SS table files. You don't see any of that. That's all abstracted for you. You have a nice seek to first, seek to last, seek to this key, forward, backwards, next, previous kind of API. Very nice, right? It ties to the transactions. So when you have a sequence number, you're only going to see the data less than or equal to your sequence number of your transactions. The seeking per source. So when so let's say you have an SS table, a lot of SS tables within the merge iterator. What's going to have to happen here is instead of sequentially seeking to where the key might be or the prefix might be, we utilize the block indexes, and the block indexes help us do an O log of n search for that specific block to set all the source SS tables to the correct block before starting iteration. So point lookups. This is basically, give me the value for a key. The way this works is per column family, we're going to start we're always going to try to get the most recent data, right? So the most recent data is going to live in the active mem table. From the active mem table, then it's going to go to the immutable mem tables, and then the disk levels, right? So the immutable mem tables, that's like L0. Disk levels is like L1, L2, L3, etc. Right? And each level has SS tables, and we're always going to try to look at the most recent SS table inside of the level, right? So once we check in memory, right, and once we start having to look at SS tables, that's when it starts to get expensive, right? And we use a nice amount of metadata within the SS table to help us determine if the key might be inside of that SS table, right? So we keep track of the min and max key for each SS table. Each SS table has a Bloom filter to tell us, if that key could exist or not, right? And if we get past those 2 points, then we're gonna utilize the block index, which is gonna give us an O log of n binary search to that specific block, the 64 KB block within the SS table, and narrows down our search. And then we have an O of K scan within the block, right? within the Klog block to find the exact key. But what's interesting here is the clock cache, right? If the block is already in memory, then we don't have to do that. We don't have to do that disk hit. We can just get a cache hit for that block. So this is kind of how the point lookups and the read path kind of work here for the point lookup. Is pretty cool and is very efficient. So the block indexes, they enable fast key lookups, right? By mapping this key range per block to file offsets, essentially. So instead of having to scan all these Klog blocks sequentially, we can do a binary search and utilizing the index and jump directly to, the 64 KB block where the key, where the key might be. The way these indexes are set up in TidesDB is they're prefix based. So each block has a min and a max up to whatever you want. The default is 16 bytes. So 16 bytes min, 16 bytes max, and it's sparsely sampled. The default is each block is sampled with a min and max, but you can set this. You can say, okay, every 16 blocks, sample a min and max kind of a thing. So this greatly assists with seek operations, those point lookups and so forth, which is fantastic. And as I stated, they're compressed, they're compact, and yeah, they're very useful. Earlier I mentioned we have this idea of key value separation. So key value separation is essentially, if the value for a key is very large, we don't want to keep it in line with the key, right? We want to put that value inside of a vlog and then put the offset only in the klog, right? So an SS table has two files, normally a klog and a vlog. The klog has 64 kilobyte blocks that store a bunch of keys, right? A key can have an inline value up to 512 bytes, but once it exceeds this value, that value is going to be put into a vlog, and the klog is only going to store its offset. So, when we go and seek to that key and we have to get the value, we're going to have to read the vlog, right? Because it's a bigger value. This allows us to store a lot of keys inside each block, thus making reads very efficient, writes very efficient, write amplification very efficient as well. You can see down here a little bit in the presentation how the klog stores data blocks, and then we have our auxiliary blocks at the end there, like the block index, the Bloom filter, and the metadata block. So compaction. One of the core problems we have here is every time we flush or do a sorted run to disk, we can have a lot of files eventually end up in level 1. Right? We don't want to have so many files. We want to try to merge these files to reduce degrading read performance, right? We to fix this, we utilize a smart adaptive compaction that merges SS tables upwards through levels. Compactions are normally triggered when L1 reaches its default threshold of 4, or when the level exceeds its capacity. Each level exponentially grows. So from the mem table, let's say the mem table is 64 megabytes, level 1 is going to be 640, level 2 6.4 gigabytes, etc. Each level grows exponentially with a default of 10x. Let's see here. We implement 3 spooky inspired merge modes: full preemptive merge, which merges an entire level at once; dividing merge, which splits work across subsets; and partition merge, which is more selective. It's like a selective key range compaction. The algorithm analyzes the LSM-tree state to choose the most optimal compaction strategy, balancing write, amplification, space amplification, and read performance. Spooky does significantly less redundant compaction work. Instead of repeatedly rewriting the same data through every level, it uses partition merging, targeting specific key ranges that actually need compaction. Instead of pre-configured leveled or tiered modes and being stuck with it, our system analyzes the current state of the LSM tree in real time and decides should we do a full preemptive merge of this whole level, or a dividing merge that splits the work, or a partition merge on the specific key ranges. The compaction strategy adapts to actual data distribution and workload patterns. It's making intelligent decisions based on what will give us the best performance right now, not based on static configuration someone set months ago. The goal is simple: efficiently merge data to maintain performance. We trigger compaction when level 1 hits an n amount of SS tables, or when any level exceeds its capacity. Then our dynamic algorithm kicks in and chooses the right merge mode. This keeps the LSM tree healthy and balanced for fast writes, fast reads, and efficient space utilization. So we don't just implement that. We also implement something called dynamic capacity adaptation. The idea is with DCA is essentially compaction determines how to merge data, and DCA determines when to add or remove levels from the structure. So level addition is primarily triggered by dividing merge when merging into the largest level, or by compaction when a level exceeds its capacity. Level removal, so triggered after a compaction again when the largest level becomes completely empty, say. Rebalancing runs after level removal or after, say, a compaction run. It updates all level capacities. This ensures capacities remain proportional to actual data distribution without rebalancing. Intermediate levels would have stale capacities after removal. Each column family has a min floor configurable, and the default is 5, up to a max of 32. The floor prevents small databases from thrashing between 2 to 3 levels and guarantees predictable read performance. Okay. TidesDB also implements this idea of control theory. When writes to a column family are very high, this can cause memory exhaustion because those queued immutables, unless they're taken care of, this is going to accumulate in memory, and we're going to have to take care of that in some way. So we have this idea of gradual back pressure. By default, each column family can have up to 10 immutables in its queue, right? But the system will essentially check how many immutables are in the queue at a certain time and start to apply pressure, millisecond pressure, to allow the immutable mem tables to flush, right? It's going to keep doing that. If it reaches like an emergency where there's greater than 10 immutable mem tables inside of the queue, it's going to really hit the brakes and wait for the immutables to flush to not cause absolute memory exhaustion. We have an L1 back pressure as well. So, the default is 4 files, and there's a multiplier here, which is a default of 3. So when you have 12 files in L1, this is also a lot, right? So there's also going to be a back pressure applied, and if there's an emergency where there's 12 files in L1, it's going to block the writes for a little bit for compaction and flush to catch up a little bit. So recovery in TidesDB is pretty interesting, right? TidesDB has to start up, it has to scan its directory, look at the column families that were previously existing, look for any write-ahead logs, look at the manifest to rebuild the level structure. So that's where the manifest comes in here, and etc. Right? So when it does all this, it could dynamically adjust the levels and do all these kind of things, right? But the manifest also keeps track of that global, it also keeps track of sequence numbers across all the levels, right? So this assists TidesDB to reinstate the sequence number that is close enough to what, let's say the last sequence number in all SS tables, the last highest one was like 42, right? Let's say, then TidesDB will read that one column family or all of them, right? If there's a lot of them, and it's going to figure out what's the greatest sequence number, and then add like a +1 to it, right? So then it has a sequence number. Um, in recovery, TidesDB looks for any corrupted write-ahead log files, looks for any corrupted SS tables, and rejects those SS tables. But with write-ahead logs, let's say the last write, it didn't validate the footer checksum inside of a block. Then we know we can truncate to the last valid block for the write-ahead block, right? That's okay. But the SS table, if it's corrupt, then we know that the other SS tables are still existing on the system. We know that because it didn't reach it didn't fully complete. So in that case, it's not matching the manifest, right? Like if we just have a random SS table there, and it's corrupted, we're gonna delete it, kind of thing. So we do that on recovery. It's very consistent, and it tries to prevent loading any invalid data, right? Data is important, and we don't want to load a corrupted SS table and then that messes up our reads later during runtime. TidesDB is fully portable, so it runs on 15 plus platforms. The database files can be shared across, x86, x64, no problem. Like you can create a database on a PowerPC and then move it onto a modern Mac OS ARM, right? No problem. So what's next for TidesDB? Well, it's to continue to stabilize and operationally test and benchmark the system, find the bottlenecks, and continue to optimize for the future. Assist others as much as we can with adoption, build a community and work with them on requests and more. Help with bindings, maybe make some official ones, and write more about storage engines and TidesDB in general. Thank you for your time, and if you have any questions, I'd be glad to answer them. Thank you.